Thank you, Atanas, for the nice presentation, for the nice introduction. Hello, everyone. Thank you to my talk about the improvement of wind turbine simulations toward exascale, energy-aware programming, and data compression. In this work, I have collaborated with some colleagues from the HPCWE project, Bruno Carmo, Lucas Franceschini, and Daniel Oliveira, the University of São Paulo, and also Richard Stevens and Luoqin Liu from the University of Twente. I'll start my presentation with a bit of the motivation. Then I will show the code and the infrastructure I have used it for the simulations. Then I will show the results for the scalability tests. Then the energy aware framework that I have used to measure the energy consumption of the simulations, a bit of the data compression algorithm, and I will wrap up with a summary. First, with the motivation, it's not so different from the other presentations that you have seen today. My part of the project is focused in the aerodynamic wakes of wind turbines and wind farms. And to study these wakes and their interaction, I have employed LES simulations. These simulations can represent better the wakes and their interactions as we see in the animation that is playing around. This kind of simulation can represent better all the scales of the wind flow. However, the computational cost of resolving the whole blade geometry of a wind turbine is prohibitively large. That's why I have used the actuator line method as an option, the same method that Professor Richard Stevens has presented, where the turbine blades are replaced by the influence over the main flow. Instead of solving the full geometry of the blades, we substitute by sections of the blade where the forces are applied. But to do the raw fidelity simulations of these wind turbine flows require a large number of processors in order to reduce the simulation runtime. However, other challenges are also related to these large-scale simulations. That's the amount of data they produce. The larger the simulation, the larger the files that you have to store, and also the high energy demand of these large-scale simulations. Then I will talk today about our efforts in the scalability, in the energy usage, and the data compression using lossy algorithms. The simulations I show you today, they are based in Wink3D. That's an open source integrated wind farm simulation framework developed by Descos et al. I will show results using this original version from Descos, and also a new version that's integrated in Xcompact 3D. Both use the finite difference method to discretize the Navier-Stokes equations. The software can model from direct numerical simulations to large eddy simulations approach with a selection of models, including implicit LAS and various subgrid scale models. We can choose up to 6th order discretization in space and up to 3rd order discretization in time. The software uses an efficient 2D decomposition algorithm that has shown scalability beyond 100,000 ranks processors. And they have a native implementation of the actuator line model. The simulations have been run in the Hawk supercomputer. That's the flagship supercomputer of the HLRS. It's an HPE Apollo system with over 5,600 nodes and 720,000 compute cores. Each node has 128 cores and 56 gigs of RAM. And I have also the compiling information about the version of the compiler and the MPI libraries that I have used for these runs. The test case I have used for most of the simulations are based in the NREL 5 megawatt wind turbine that also have been presented by other colleagues from the project. The domain size I have used for these simulations is 80 diameters in the length and 5 diameters in the span-wise direction. And the wind turbine is placed 3 diameters from the inflow condition. The grid resolution is what for us is the medium resolution is 1024 in span stream-wise and 512 elements in the span-wise directions, summing up to 268 million elements. Here we can see the scalability, the results of the scalability tests comparing the original Wink 3D and the newer version XCompact 3D. They use both softwares use the same actuator line model code. We see a large increase in computational performance where the blue bars represent the clock time, so the simulation time per time step of the new XCompact 3D, and the orange ones from the original version of the Wink 3D. We see that's a large increase in the computational performance between 49 and 57%. In this graph, we see not the computational time, but the relative performance. And we see that the scalability of the codes is good until this 4,000 ranks, 4,000 processors, but it's far from the ideal line when increase the number of processors to 16,000. But we can also see here it's the curves are not far from each other, but we see that the speed up is better using the new version XCompact 3D compared to the orange one for a specific amount of ranks. This is these 32 nodes with 4,000 ranks. Here we see the results from that were plotted in the last graph, and we see that using this specific amount of processor of ranks, we get 18% better runtime. And more tests have been conducted to understand the reason why the new version is specifically more efficient using this amount of processors. To that, I have used a performance metric. That's the elements solved per second. These experiments have been done in one node of the machine, and the number of grid elements per rank is divided by the clock time that we need to solve one time step. Then in this metric, the higher the metric, the better the performance is. And we get it, so we get these results varying the grid size of the simulation in one node. And we see that for the old Wink 3D, the performance is around a bit above 30,000 elements solved per second, but it's pretty stable across the number of the grid elements that I solve. But the new version has a much better performance. We see here that we can solve up to 80,000 elements per second, but we have a peak. Yeah, so here the grids are larger. When we decrease the grids, we get better performance. When we continue decreasing the grid size, then the performance degrades a bit. That's not uncommon. That's normal behavior for HPC software in these new architectures. But the difference between using more grid points or less grid points, so the best amount of grid points is we get a 28% more efficient. For reference, I have run the simulations without the actuator line model. Then there are simulations without the wind turbine. And we see that the performance increases with decreasing grid size, but then they stabilizes. They do not fall, as we have seen when we have the simulation using the actuator line model. Here the comparison, the blue line without wind turbine and the orange line with turbine modeling. And we see a great impact, mainly in when we have less elements. Yeah. And the reason for that is that the actuator line model calculations are local to each grid partition and they are not parallelized, which cause problems in the massive parallelization, which is dictated by Amdahl's law. Here we see the results when we increase the number of grids in the number of nodes. Here in blue, elements of per second in one node. In orange, the curve using two nodes, and the points here is using an increasing number of nodes, so 8, 32, and 128 nodes. We still get acceptable performance of 76% with 32 nodes, which corresponds to 65,000 elements per rank, grid elements per rank. The summary from this scalability test is that the XCompact 3D, the new version, showed a significant improvement in computational performance compared to the old one. Using a performance metric, we have found that the code is most efficient when using this 65,000 grid elements per rank, which is up to 28% more efficient than using other grid sizes. Just a remark, this was tested in the Hawk supercomputer. This figure, this 65,000 grid elements per rank can be different in different systems. And the simulation with this 268 million grid elements showed acceptable performance up to 5,000 ranks, 4,000 ranks. Now I move for the results of the energy-aware framework. So the energy usage of the supercomputers is continually increasing, which is an issue that can be addressed, for example, using an energy-aware programming framework. The energy usage of a simulation is correlated to the efficiency of the code in a single node and also to the parallel efficiency of the large runs. However, it's not always true that the simulation with the shorter runtime is the most energy efficient. And to study that, we have used an specially instrumented computer cluster that has been developed in the UE project Access. And I have to thank my colleague Dimitri Kabi for to get access to the system. And what we have here, we have a node, a compute node with external power measurement system. And here is a diagram of all the instruments that have been used to measure the power consumption of the machine. This is this one uses a different architecture than the ROC supercomputer. They use dual Intel Xeon processors that are a bit old, and But anyway, with the instrumentation, we could measure the energy usage. In this, for these simulations, I have used not the NREL test case, but the test case of the Swift benchmark. That's a bit smaller. This Swift benchmark was coordinated by the International Energy Agency. They have measured the turbine and also wakes in a flat terrain, and they have used this modified Vestas V27 wind turbine generators. From this benchmark, we have power and load measures in a series of atmospheric conditions. In this case, the grid spacing is also varied, changing the number of elements per core. We start up with a bigger grid of about 4 million grid elements, and we decrease it to a grid of 260,000 grid elements, having the span from 176 grid elements per rank down to 11,000 grid elements per rank. The time step is the same for all simulations, 0.05 seconds. And for these simulations, I have used the new version of the software XCompact 3D. And the logs generated by the access cluster are treated using a Python program. And what we see here is the plot of these results. We see in blue the energy used, the current used by the memory banks, and in red we see the current and also the energy used by the both CPUs of the server. And we can see two different phases here. We have, once the simulation has started, we have this initial phase where the input file is read and the simulation is prepared, where the energy consumption is not so high. And we have the simulation run phase where the both energy consumption of memory and processor goes up. Here we have a zoom in the initial phase and show the first 4 time steps. Between the time steps, we have a drop in the energy consumption of the processor that is correlated to the phase where the different processors have to communicate and then they start processing. Here are the numerical results, but the results are better seen when plotted. Again, we are seeing the performance metric. The performance metric is the highest. That's the blue curve. The performance metric is the highest using the less amount of grid elements per rank. That's a bit different figure when using the Hawk supercomputer. We have seen that the blue curve, we had a maximum and then it dropped when we have decreased the number of grid elements per rank. And in this case, it was the best performance metric was when using the least amount of grid elements per rank. However, the energy usage show a different perspective. So the energy user is higher when we have more elements per rank, then it decreases, and then for the last points where the grid is smaller, we have a jump in the energy. Yeah, and this energy is the energy in joules divided by the number of elements solved. And we can see from this metric that the performance is 26% better this we're using 11,000 grid points per rank instead of using 160,000. But the usage is better using the grid with 22,000 elements per rank. And summing up, the results of the study using the energy-aware framework showed that we can spare 18% of energy using a specific number of grid elements per rank compared to the simulation using the highest grid element count in this machine. However, from a purely runtime perspective, an even lower number of elements per rank would be better, but it results in a 11% higher energy consumption compared to using 22 grid elements per rank. Then moving to last topic for my talk about the data compression. The motivation for the data compression is that the development of the file storage technology has historically grown slower than CPUs, which has resulted in a discrepancy between the storage capacity and bandwidth compared to the computing capacity of the big HPC systems. And this trend that tends to get worse in exascale systems due to the large computing power that will be available, mainly due to the use of accelerators. One way to alleviate this problem is to compress the generated files, which then occupy less storage space and use less bandwidth to be transferred. Several lossless compression techniques have already been proposed. That's what some that we use in our daily life, like zip files or GZ files, and they are based in dictionary encoders or preceding predictors stage to decorrelate intrinsic spatial redundancies. Yeah. A different approach is to adapt the lossy compression algorithms that have been used, for example, in image standards like the JPEG 2000 codecs to floating-point arrays. We have seen a similar approach yesterday in the talk of Jean Ray, when he showed also the use of wavelets for the applied to images. I'm also applying wavelets here, but I'm not studying the wavelets themselves. I'm using the wavelets to I calculate the wavelets, store them, and then if needed, I reconstruct the original data set. It's a bit different approach than G-Rain. I have used it for that the Big Whoop library that's developed by my colleague Patrick Fogler, that uses a highly efficient wavelet-based compression scheme. My work has been to adapt this library to handle the XDMF format used by Wink3D and XCompact3D. A bit about the compression algorithm. So the first step is to transform the floating point array of the CFD results that we have. There are real numbers, so there are floating point numbers to integer array that we have used this fixed point number format Q. Yeah. Why we do that? The JPEG 5000, okay, got freezed. Moment, please. Hello, can you hear me?
Yes, we can, Flavio.
Okay, so
But remember that you're running out of time as well. For this reason, I show my face. Sorry.
so I'm almost at the end. It's no problem. So then from this, we have the floating point numbers. Then we change that to integers, calculate the wavelet coefficients, and we get the compressed data stream that's then stored in the storage system. Oh, again. Sorry about that. I don't know I cannot change the slide. I don't know why.
Well, you are the expert, so now you lost your face.
Okay, again, so it's my notebook. Yeah, so I should have run in the bigger machine, not in my poor notebook. Again, I have used the Swift benchmark for that, and I have tested in a small grid and in a large grid with compressions ratio of 20:1 and 60:1. That then the final files have 5% or 1.6% of the original size. And I see that naturally with the lossy compression, we have a loss of information that's created by this compression. Here we see the profile of the axial velocity over a point with 30 meters high. We see that the large scales are good captured, but we have, for example, in this region here, a small discrepancy due to the compression. And to show that in more detail, I have done a Fourier transform of the velocity signal that we see that in the large scales, we have a very good representation, but when we have a big loss of information with a high frequency range. But it's not so dramatic. So here we see contour plots of the axial velocity. We see that from a visual perspective, we cannot see with our blown eyes, so the difference between the compressed and the original datasets. So we skip that and jump to the conclusions that we have seen the aspects of the high fidelity simulations, the amount of data produced, and also the high energy demand. And we have faced these two aspects have been selected for the optimization, and we could use a lossy compression algorithm that could compress the data with a compression rate of 60:1 with good results. And we could save up to 18% energy selecting the right amount of grid elements per rank. So thank you very much, and I'm happy to answer any question that you have.